Hello everyone, welcome back to my channel. Today we're going to go over this problem of fluid mechanics. So water in an 80 millimeter diameter jet with a speed of 20 millimeter per second to the right is deflected by a cone that moves to the left at 15 meters per second. Determine the thickness of the jet sheet at a radius 200 millimeter and the external horizontal force needed to move the cone. You may ignore gravity. So basically, first things first is to choose our control volume. And I'm going to choose our control volume as this. Um, and this control volume will actually help us solve for the thickness of the jet sheet because uh, the surface area at that point of the control volume boundary is going to be um, the thickness of the jet sheet. Is going to correspond to the thickness of the jet sheet, basically. And yes, now we have to apply conservation of mass to the control volume, using a coordinate system that is fixed to the cone. And we note that the control volume actually moves with the cone. So this is going to be a non-inertial reference frame. And we can first draw a free body diagram. So the coordinate system is fixed to the cone as such. Basically, this is X and this is a Y, and it moves with the cone. And the equation for conservation of mass is going to be d over dt, control volume of rho dv, plus the integral over the control surface of rho times relative velocity times dot dA. And this is equal to 0. So in the chosen frame of reference, basically as the cone moves, and since the coordinate system is fixed to the cone, we're in a location of steady flow, of steady state flow. So this one is going to be 0. And now we have to find what this represents. Basically, we have to find the integral over the control surface of rho relative velocity dot dA. And this is equal to 0. Um, and this will be equal to uh so this will be equal to, let me see. The integral, okay, wait. Do we have to integrate? It'll be rho, but what is the relative velocity? The relative velocity is the velocity of the jet stream relative to the coordinate system. And since our coordinate system is attached to the cone, and the cone is moving at speed vc, the relative velocity is going to be um, vj minus vc, because basically our positive x direction is taken to point to the right, and vj is moving to the right at this speed. And relative velocity, like for instance, this is let's call it vj relative to c. Vj relative to c is equal to vj minus vc, but since vc is negative, since it's pointing to the left, we have negative vc, negative negative, which is positive. So this becomes vj plus vc. So vj plus vc. Yeah, so that is what the relative velocity represents. And we are going to multiply it by dA. And dA in this case is the surface area of this face, which is, if we zoom in, um, going to be the area of a circle. And the area of the circle is going to be pi r squared. Um, and we know that the jet diameter is 80 millimeters, so we can call the jet diameter dj. And dj over 2 is going to be the radius. So this is going to be multiplied by pi times dj over 2 squared. J over 2 squared. And yes, so it's going to be that. Okay. And actually, it's going to be negative since this surface area is pointing outwards and is opposite the direction of flow of Vj. So because this is a dot product, so if the arrows are pointing opposite each other, it means the angle between them is 180. And cosine of 180, which is in a dot product, is going to be -1, which will make it negative. Okay, so now we have the first part. And there are two exit points, as we see over here. There are two exit points over here. However, mm, we have to keep in mind that this is actually three-dimensional. So this means that we're gonna have to look at the control volume as more closely, something that looks like this. And it's gonna have thickness of this. This is gonna be our control volume. So let me see. We're gonna add a rho times the relative velocity of jet stream relative to that time plus rho v. Basically, let's call the velocity at which it exits v to make it easy. So this is gonna be rho times v. And it's going to be a positive add because the control volume is going to be have a surface area parallel with the surface area vector. And the surface area is this area over here. That's the surface area of our control volume. The surface area is going to have a vector that points in the same direction as this v. So it's going to be positive. So we have rho times v times the surface area of this control volume, which is going to be 2 pi r. Yeah, so, and we call r this distance over here. So this distance is going to be r. And basically this v is the speed using the coordinate system x, y, z. Yeah. So basically, we know that this is r, so the surface area will be equal to 2 pi r times t, because t is the thickness. And it's going to be times 2 pi r t. And now we are going to simplify this equation a little bit. So we're going to simplify it as, oh wait, hold on. Yeah, I think I forgot to add a negative sign here, but I think I explained why it was negative. So it's going to be negative rho times Vj plus Vc times pi dj squared over 4 plus rho v 2 pi r t, and this is equal to 0. So solving for t, we have that it is equal to rho times Vj plus Vc times pi dj squared over 4 divided by rho v 2 pi r. And the rows cancel out. And what else cancels out? I think this simplifies to 1 over 8 dj times Vj plus Vc over V times dj over R. Because the pi's cancel out. And to find V, which is the velocity at the exit, we can apply Bernoulli's equation along a streamline because it says that yes, because it flows in a streamline. Basically, that is why we can apply Bernoulli's equation. And Bernoulli's equation has several assumptions. Bernoulli equation assumes steady flow, no friction. That means that viscous effects are negligible, that it flows along a streamline and it's incompressible flow. So we can apply Bernoulli's equation over here to find V. Basically, we can start at point 2, the location that is exposed to the atmosphere, which is called this point 2 over here. So point 2, and this is point 1. Point 2 is at the exit of the volume from the control volume, and point 1 is when at the entry point of the jet stream. So basically, by Bernoulli's equation, the pressure over rho g plus v squared over 2g, and this is just generally right now, plus um z, okay, is equal to pressure over rho g plus v squared over 2g plus z at 1. Basically, it's energy conservation, and what it says is that the sum of the energies over here at 2 must equal to sum of the energies at point 1. Because basically, if pressure increases, or wait, when velocity increases, for instance, pressure decreases, I believe. And as we saw earlier in one other video, Bernoulli's principle is like this. So it's like this. So the energy per unit volume before is equal to the energy per unit volume after. And over here we have a similar problem as the problem we have. Basically, um, it's dealing with flow and it's dealing with flow that decreases in diameter or decreases in thickness. So back to our problem, um, using a frame of reference fixed to the cone, so the system is in steady state. Because I believe that for Bernoulli's equation to apply, your system have to be in steady state. Let me verify that. Yes, a fluid system must be in steady state for Bernoulli's equation to be applied correctly, meaning the fluid velocity at any point within the system cannot change over time. If the flow is not steady, fluid properties like velocity and density will vary with time, and Bernoulli's equation, which assumes steady conditions, would yield incorrect results. So in this case, in order to apply Bernoulli's principle, we have to use a frame of reference fixed to the cone, as we have done from the beginning. So that the system can be considered in steady state. So using this frame of reference, uh, let me see. So let's consider the pressure at point one. So the pressure at point one is basically just um atmospheric pressure. So atmospheric pressure is actually zero gauge. And basically let's first write out these equations explicitly. P2 over rho G plus V2, which is actually just V from our equation or from our diagram, over 2G plus Z plus Z2. Z2 is the elevation of point two from basically the coordinate system. And that value is so that value is actually gonna be, I believe, this height over here, but we're not really told gravity because it says you may ignore gravity. So that term is negligible. So we're just gonna use the equals 0. Um, okay. And this is equal to the pressure at 1 over rho G plus V1 squared over 2G plus Z1. So Z1 is also going to be assumed to be 0, um, as we did for Z2. And pressure 1 is also at atmospheric pressure, because it's exposed to the atmosphere. So we will do zero gauge pressure for both of them. So both of these terms disappear, and we're left with simply V squared is equal to V1 V squared equals V1 squared. So let me see. So this means that V is equal to V1, and V1 uh is equal to Vj plus Vc relative to the coordinate system on the cone. And now plugging in these values in for V for our equation for T, we have that T is equal to 1 over 8 dj times Vj plus Vc. And then we plug in Vj plus Vc for V. So Vj plus Vc, and then times dj over R. And this is equal to dj squared over 8R. And we plug in the given values, which is that dj is equal to 80 millimeters and R equals 200 millimeters. So this is equal to 0.08 meters, which is 80 millimeters squared, over 8 times 200 millimeters, which is 0.2 meters. And if we calculate this out, we get that T is equal to 4 times 10 to the negative 3 meters, or 4 millimeters. And that matches the value we were supposed to get. Now we want to find the external horizontal force needed to move the cone for part B. And this part is going to be conservation of linear momentum. And let me see. So for the first part, even though we fixed the coordinate system to the cone, the control volume is not moving relative to that reference frame that we fixed to the cone, because the control volume is actually moving at the same rate as the reference frame. So it is not moving relative to the coordinate system. But even if we did not use a non-inertial reference frame for part A, the control volume would still be moving. And this is important distinction to make, and I'm going to make it right now. Basically, the key difference is to recognize the two separate ideas. We have a reference frame concept and a control volume concept. So the reference frame concept means that it involves the coordinate system in which we apply Newton's laws. And the effective equations is if it determines whether fictitious forces appear. And the control volume is the geometric region across which you apply mass and momentum balances. And it determines what surfaces mass flows through. So we can have a fixed control volume in an inertial frame, like a standard nozzle problem, a moving control volume in an inertial frame, like the cone problem here, or a fixed control volume in a non-inertial frame, which is the cone attached frame, if the cone accelerates. Uh, so we're analyzing the problem in the inertial lap frame. The ground doesn't accelerate, so Newton's laws are valid directly, but the control volume is drawn around the moving cone. This means the boundaries of the control volume move through the inertial frame with the cone's velocity Vc. So the reference frame is still inertial, and the control volume surface moves inside that inertial frame, and that's completely allowed. Yes. So basically, this is an important distinction. And I asked why they chose an inertial reference frame for the momentum equation. Basically, the inertial frame is one that is not accelerating. And by using the inertial lap frame, we avoid introducing any fictitious forces, and the momentum flux terms can still use relative velocity to express the flow rate through the moving control surfaces. And the resulting equation stays physically correct in the lap frame, but uses the convenience of relative motion to the cone. So it really is just a way to account for mass flow through a moving control surface while keeping the overall reference inertial. So yes, there are two valid ways to write the momentum equation here. We can use an inertial frame with a stationary control volume, where the control volume is fixed in the lab and water enters with Vj and leaves with the lab frame velocity V out lab. And the cone moves through the control volume. And this is what they chose, and the linear momentum equation remains in its normal form. We can also choose a non-inertial or cone-attached frame where the control volume moves with the cone, and in this frame, the flow appears steady. However, the momentum equation needs correction terms for the relative velocity and possible fictitious acceleration forces if the frame is not inertial. But since the cone is moving at constant velocity, it's not accelerating and no fictitious forces appear. Still, it's more rigorous and safer to formulate in an inertial frame and then switch to relative velocities algebraically, as we did here. Let's think through why we chose a coordinate system fixed to the cone for part A. It was to simplify certain aspects because if we can assume that the flow is streamlined and at steady state, and that's something that we can only do if our coordinate system, our frame of reference, is fixed to the cone. If the frame of reference were not fixed to the cone, the flow cannot be modeled as a steady state. So, yes, in a fixed inertial frame, the flow around a moving cone is unsteady. Um, so that is why it is helpful to choose a non-inertial reference frame for the first part of the problem. Basically, since we are able to model the flow as steady state, one of our integration terms disappears, which is very nice, which this term disappears. And if we had not assumed steady state, we would not have been able to apply Bernoulli's equation to solve for this V over here. But for part B, a non-inert an inertial reference frame is more beneficial. Um, yes, so we're going to apply conservation of linear momentum uh, only in the x direction because only momentum in the x direction, well, momentum in the x direction is conserved, as you can see here, and so is momentum in the y direction, but the momentum in the y direction just cancels each other out. Um, but we are curious about the horizontal force, not the vertical force. So that's going to be conservation of momentum in the x direction. So we're going to use the same control volume, but using a coordinate system that is inertial, so not fixed to the cone. However, the control volume will still be moving with the water as the water changes. So for conservation of linear momentum, we have d over dt over control volume times the velocity in the x direction times rho dv plus over the control surface times ux rho u relative dot dA. This is equal to the body force in the x direction plus the surface force in the x direction. And because of steady um let me see. So I was actually wondering why the flow could still be modeled as steady state even in an inertial frame. Um is because even though we're formulating everything in the inertial frame, it allows for time-dependent control volumes. So when the control volume moves in such a way that the field inside is uh steady relative to that motion, the derivative of the integral is still zero in the inertial frame description. So imagine you're standing on the ground, an inertial frame, but a cone moves at left at constant velocity, deflecting a water jet. Uh, Draw a control volume that moves left at VC. So it's wrapped around the cone as it moves. Um, Here the control volume is sliding left, but inside it, the flow pattern does not change with time. It's a steady persistence of new fluid through the same geometry. So therefore, it equals zero because the amount of momentum, mass, etc. inside the moving region remains constant over time, even though the region itself translates. Uh, so let me see. Key conceptual separation. So quantity is the flow field around the cone. Is it steady in the lab? No, the cone moves through space. Is it steady in the moving control volume? Yes, because the shape and relative speeds are fixed. Quantity. Control volume around cone. Is it steady in the lab? Moves at constant speed. Is it steady in the moving CV? And moves with cone. So yes, I think this answers the key question. So I guess I was formally wrong to say that the reason why we used a non-inertial reference frame is in part A is so that we can consider it as steady state so that this term can be zero. But I do think that it was necessary in order to apply uh Bernoulli's equation in that particular case. So when we were using relative velocity is defined as the fluid velocity measured in the chosen reference frame. Here it is the inertial lap frame, and VSCS is the velocity of the control surface. So V relative is equal to the fluid velocity minus the velocity of the control surface. So in summary, I think that choosing the frame of reference as non-inertial in part A was beneficial in so that we can apply the Bernoulli equation because the Bernoulli equation only applies for steady state flow. And steady state flow relative to the ground, uh, in the previous problem, is only when we choose a frame of reference attached to the cone. Okay, so here we're going to use a inertial reference frame. And thus, this one is still steady state because what this one is saying is that relative to the control volume, is the mass in the control volume changing with time, or is the volume changing with time? And the answer is no, because what comes in goes out. However, we will have a non-zero for this term because it determines like which volume goes in and which goes out. So for integral over the control surface of ux times rho u relative dot dA, we have that is equal to what is ux? Well, ux at the inlet is equal to Vj plus Vc as we saw. And basically this is going to be ux, which is at the inlet, is relative to the control volume frame. So yeah, it's going to be equal to Vj plus Vc and times what did we see previously was, yeah, So negative rho times Vj time plus Vc times pi times dj squared over 4. So we're going to multiply it by negative rho times Vj plus Vc times pi times dj squared over 4. And we're going to add the x component of velocity at the exit. So that one is going to be equal to um going to be equal to v cosine theta at the exit. So plus v cosine theta, and then multiplied by what was there. So multiplied by rho v times 2 pi rt. Rho v times 2 pi rt. And also, since this is going to be equal to the body force in the x direction plus the surface force, or no, sorry, the body force plus the surface force. So there's no body force over here, and the surface force is going to just be from the cone. And it's going to be the external horizontal force needed to move the cone. And that force will be opposite in magnitude to what Fs is because of Newton's third law. So we have no gravity because gravity is negligible here. And Fsx is going to be equal to negative F, which is the force needed to move the cone. We're going to, sorry, no, I mean like the force of the cone on the stream of water is going to be F. So Fsx is going to be the force needed to move the cone, which is equal to negative F. So let me see. So substitute the what we found for V. So V is equal to Vj plus Vc. We're going to substitute in that for V. And also simplify the equation a little bit. So simplifying, we have that F is equal to rho times Vj plus Vc squared times pi dj squared over 4 minus rho times Vj plus Vc squared times cosine theta times 2 pi rt. And plugging in known values, which is a rho is equal to 1000 kilogram per meter cubed. Vj is equal to 20 meter per second. Vc is equal to 15 meter per second. And theta is equal to 60 degrees. We find that F is equal to 3080 newtons. 3080 newtons. So that is the end of this problem. I hope that this problem was helpful for you guys in understanding more about how to approach these reference frame problems. I'm sorry for the confusion in this video. I know it was kind of all over the place, but I'll be posting the slides, so hopefully that'll be helpful. Yeah, see you next time.